Okay. So the next thing that we have here is the inverse of a matrix by elementary operations. Inverse of a matrix by elementary operations. There was actually a lot more about matrices. Maybe we will do that in the next chapter. I'm not really sure, but as long as I can remember, there was a lot more about matrices in the first semester of any typical engineering course that you might take up, but I suppose that comes all in the next chapter of this book. Okay, so now the inverse of a matrix by elementary operations. Now let X, A, and B be matrices of the same order such that X is equal to AB. So let X, A, and B be matrices of the same order. Matrices of the same order such that X is equal to A times B. In order to apply a sequence of elementary row operations on the matrix equation X is equal to AB, we will apply these row operations simultaneously on X and on the first matrix A of the product AB on RHS. So I don't want to write everything down. So again, in order to apply a sequence of elementary row operations on the matrix equation X is equal to AB. So of course you have to apply them on both sides of the equation. So you can apply basically these row operations simultaneously on X, which is the LHS, and also on the RHS. You can apply them on the first matrix, for example, A of the product AB of the RHS. And similarly, in order to apply a sequence of elementary column operations on the matrix equation X is equal to AB, we will apply these operations simultaneously on X, which is the left-hand side, and on the second matrix of the product AB on RHS. So the column operations will be, if you're applying any column operations, the column operations will be applied on X and simultaneously on B. Row operations will be applied on simultaneously on X and on the left-hand side matrix A. And that is because of the way that we do actually matrix multiplication. Because, for example, if you have some matrix A that has these, for example, elements, you have this matrix over here, let's call this A, for example, and you have this matrix B, for example. And when you have these matrices and they are being multiplied together, when you do the multiplication, what you always do is that you take, for example, one row and multiply it by a column. Again, another row, the same row, another column, the same row, another column, and so on and so forth. And that this would be step 1, this would be step 2, and this would be step 3. And moreover, you will have, for example, the second row, and then you would have first column, second column, third column, meaning that you would have basically 4, for example, 5 and 6, and then you have again this row here, and that would be basically this operation, and this operation, which is 7, 8, and 9, right? So that it makes sense that the row operations are, if you have a matrix equation of the form x is equal to AB, so the row operations will be performed on basically x and on A, because A is basically in this equation is dealt with row wise. But then basically when you're doing column operations, it makes sense that you do it, that you do that on x and b simultaneously, because as you can see, the matrix B is being dealt with column wise. So that way it does make sense. So now, in the view of the above discussion, we conclude that if A is a matrix such that A inverse exists, then to find A inverse using elementary row operations, write A is equal to IA and apply a sequence of row operations on A is equal to IA till we get I is equal to BA. The matrix B will be the inverse of A. Similarly, if we wish to find A inverse using column operations, then we write A is equal to AI and apply the sequence of column operations on A is equal to AI until we get I is equal to AB. So what this means is that, having all of what we said in mind, now if you have if A is a matrix, if A is a matrix such that A inverse exists, to find A inverse using elementary row operations, what you will do is that you will write A as A is equal to I times A, and then of course then the elementary row operations will be applied to A and I simultaneously, and you keep doing the same thing until you get I is equal to B times A. I is equal to B times A. On the other hand, if you wish to find A inverse using elementary column operations, you need to write A is equal to I times A, so that A becomes the second matrix. And if A becomes the second matrix, then you can do the column operations on A and on AI, actually. Has to be AI. A is equal to A times I. Not like that, but like this. So that the elementary column operations are basically applied on A and on I simultaneously, and you keep doing the same thing until you get this equation in the form I is equal to AB. And which one, basically whether you do this one or you do this one, depends on the structure of your matrix. If basically the structure of your matrix is such that it's easier for you to do basically row operations, then you will do row operations. if it's easier for you to do column operations, you will do column operations. Sometimes it's actually not really possible to do row operations. You have to do the column operations. Sometimes it's not possible to do column operations. You have to do row operations. And sometimes it would be very tedious to do either of them. So then in that case, you need to use some other techniques that there are, because then calculation would be very would not simply be so straightforward that anybody can do it. And therefore, of course, there is techniques for that I think we will cover them in the next chapter of this course, basically this book. But for now, we will do a little bit of basically manual work until we get to learn those techniques. Now, as a remark, in case after applying one or more elementary row or column operations on I is equal to A is equal to IA or A is equal to AI, if we obtain all zeros in one or more rows of the matrix A on LHS, then A inverse does not exist. And there is a reason for that, because then you will get so what the remark is that suppose that in case after applying one or more elementary row or column operations, one or more elementary row or column operations on A is equal to IA, or on basically for column you have row or column. Let me actually write this properly. So elementary row or column operations on so this would be related to row operations, and column operations would be A is equal to AI, meaning that the operation will be done simultaneously on A and I. If we obtain all zeros in one or more rows of the matrix A on LHS, if we obtain zeros on in one or more rows, in one or more rows of the matrix A on LHS, then A inverse does not exist. Now you need to keep this remark until we get to the proper example, so that I can show you what the reason for that is. Otherwise, this way there is no way to really understand it, right? But that is actually true. So now, when I was in college, this was my favorite thing to do. Of course, it was many years ago, But well, it was my favorite thing to do all of these column operations, these row operations, and these matrices. Okay, so now let's do an example here. Let's basically example number 23. Example number 23. So you want to using elementary operations. Using elementary operations, we want to find the inverse of the matrix A is equal to 1, 2, 2, and negative 1. So basically you can do this in two ways, of course, using row operations and using basically column operation. Okay, so now that we have an example, we can actually talk about all of the things that we talked about writing A as, for example, I times A, or writing A as, for example, A times I, and so on and so forth, and doing row operations and column operations on these matrices or on these equations. We can understand them much better using an example. So basically you can either do row operations or column operations on these matrices. For whatever reason, diagonal operations are, as far as I know, are not defined, probably because it wouldn't work in the way that basically matrix multiplication has been defined. But these row and column operations work mainly because my matrix operation has been defined that way, so we have no problem with that. Now, basically, if you have any matrix A, you can write it as A times I, which is the same thing as A, or you can write the same matrix as I times A. And now, depending on what you want to do, of course, you write it this way or this way. Now, if I write my matrix this way, it's possible for me to do row operations on this equation. And the reason for that is that basically when you do row operations, the way that we do matrix multiplication, you have this matrix over here, for example, 3 by 3, and then you multiply the same matrix by this matrix, right? So when you do matrix operation, the way that we do matrix multiplication is that we take this row and multiply it by this column. So this is the row, and this is column 1, and then we do the same thing for column 2. We do the same thing for column 3, and so on and so forth. And then we move to, basically this is row 1, and then we basically move to row 2, and then again basically column 1, column 2, column 3 again, and then we move to basically to row 3, and then we move to column 1, column 2, and column 3, and that way we do matrix multiplication. That means that basically the the row operation can be done on the matrix that you have on the left in the multiplication. The column operation can be done on the matrix that is on the right in matrix multiplication. Now, so having that in mind, when I have my equation in the form A is equal to IA, what happens is that basically I can do row operation on this matrix. On this matrix I can do row operation. And I can do row operation on this matrix. And I can do row operation on this matrix because it's a matrix which is left alone. I can do whatever I want to do on that. And whatever I do here, I have to do the same thing on the other side of the equation as well. Meaning that, and over here, I'm allowed to do only row operations. And therefore I write my matrix this way and I do row operations. Now, when I have written my matrix this way, A is equal to A times I, so I can do column operations on the matrix on the right, as you can see, and now I has been written on the right, so I can do column operations on I and column operations on A, and both sides of the equation would be exactly the same. And so here I have basically column operations. Now what happens is that basically, now what is the goal of doing all this? The goal of doing all this is to basically, for example, take any of these equations, for example, A is equal to AI, and when I do column operations of course I do it on this matrix, and this, and basically what you will do is that you have to do as many column operations as required so that this looks like I. And then depending on what you do here, you do some column operations here on I as well, and I becomes some other matrix. I becoming some other matrix means that you can think of I as some matrix B, for example, because I changes to some other matrix. It's not the identity matrix as well. And then the whole equation will look like A times B is equal to I, because now this matrix on the left has become I. And from this I can basically conclude that basically B is the inverse of A. You can conclude that B is the inverse of A. On the other hand, when I have this equation over here, A is equal to I times A, what happens is that here we said that we would do row operations, and the row operations would be done on this matrix I and on this matrix as well. So when I do row operations on these two matrices, I do row operations on A primarily in such a way that A becomes exactly I. And depending on what I do here, I have to do the same thing over here as well. And then this matrix I becomes some other matrix, for example, something like B. And then this equation, you can think of this equation as B times A is equal to I, and therefore you can say that B is the inverse of A, and that way you have found the inverse of A in this case, and you have found the inverse of A in this case. That's basically the whole story here. Now let's do this in the case of basically this matrix over here. So basically the matrix that I have is A is equal to 1, 2, 2, and negative 1. And I want to basically find the inverse of this matrix using row operations. Using row operations. Using row operations means that the operations has to be done on the matrix on the left, right? So the matrix on the left, I write it as I, and I want to do all of the operations on the matrix I, and then I multiply this I by A, and that gives me again, basically, A, of course, right? So I can write this as A is equal to I times A. That's the same thing. I've just taken this to the other side, taken this to the other side. And therefore, I know that my A is equal to, now what happens is that my A is basically 1, 2, 2, negative 1. 1, 2, 2, negative 1. And I is basically the identity matrix 1, 0, 0, 1. And A is some matrix A. We don't really care about that because we are not doing any operations on this. These are row operations done on the matrix on the left, and also on this matrix. Now, how do I decide what sort of operations I need to do in this particular case? So in this particular case, the kind of operations that I need to do depends on what I need to do so that this matrix 1, 2, 2, negative 1 looks like an identity matrix, looks like this matrix here, which is 1, 0, 0, 1, right? Now, for example, the first thing that I need to do, that an identity matrix is 1, 0, 0, 1, meaning that this remains a 1, this has to become a 0, this has to become a 0, and this has to become a positive 1. Which means that, for example, if I apply, for example, R2, these are all different types of transformations that we talked about in the previous video. So I take the row 2 and subtract 2 times row 1 from that. I take row 2 and basically subtract 2 times row 1 from that. So if I take R2 and subtract 2 times row 1 from that, for example, 2 times 1 is equal to 2, and then 2 minus 2 is equal to 0, meaning that I will get a 0 over here, right? So that's the step 1 in order to get a 0 over here. So if I apply this, what I will get is basically, so this matrix becomes, the first row is, of course, remains the first row, which is, I'm not making any changes to the first row, so I write it as 1, 2. And the second row becomes, for example, this 2 becomes 2 minus 2 times the corresponding element in row 1, which is equal to 1. 2 minus 2, which is equal to 0. And then I have this negative 1 minus 2 times 2, and that gives me negative 1, negative 4, which is equal to negative 5. And that is equal to this matrix that is equal to this matrix 1, 0, 0, 1 times 8. So that was some first step that we did in order to get, in order to make this a 0, so that, and I have to do this step by step so that this matrix looks like exactly an identity matrix. So now this 1 is okay. I need a 0 here, and I need a 1 over here. Now the next step that I have is I can apply, for example, in order to make this a 1, I can multiply this row by a negative 1/5. So I take R2 and write it as negative 1/5 times R2. So if I multiply negative 1/5 times negative 5, that would be a 1, and then negative 1/5 times the 0 is equal to 0. So the only thing that happens is that this becomes a 1, which is what I want, right? Which means that basically I will write the first row as it is. I'm not making any changes to that. This remains a 0. This becomes a 1, and of course, something that I forgot here is that, of course, whatever you do on this side, you have to do on this side as well. Meaning that I have to actually do the same thing on this matrix as well. So now if I write, for example, the first row remains the same, 1, 0, and as you can see, this matrix is now changing, becoming some other matrix. So R2 minus 2 times R1. So 0, for example, minus 2 times, for example, 1 is equal to negative 2. Or basically 1 minus 2 times 0 would be equal to 1. This remains the 1. And that is basically that, right? Now, of course, it doesn't really matter what happens here. Whatever you get here in the end of the steps, once you have this matrix in the form of an identity matrix, then this, whatever this becomes, is the inverse of A automatically. So what that means is that now if I apply R2 minus 1/5, R2 becomes negative 1/5 R2. So that means that the first row remains the same, 1, 0. And the second row, negative 1/5 times negative 2 is 2/5. And negative 1/5 times 1 is equal to negative 1/5. And that is a 0 over here, times A. Right, so that is that. So now my matrix over here is, I have a 1 over here and a 1 over here. We have no problem with that. There is a 0 over here, which is okay. There is only this 2 that needs to be taken care of. So now if I apply, for example, R1, and on R1 I will do basically R1 minus 2 times, for example, R2. So if I do this, I take this R1 and subtract from that 2 times 1, and that becomes a 0. And I take this, basically this 1, and subtract from that 2 times 0, in which case I will left with the 1 itself, which is absolutely what I want. I don't want I don't want this 1 to be changed, right? So now if I do that, what I will get is that R1 becomes R1 minus 2 times R2, which is basically so basically 1, for example, minus 2 times 0 is equal to 1, and 2 minus 2 times 1 is equal to 2 minus 2 is equal to 0. So this row becomes 1, 0, 1, 0, and the second row doesn't change, 0, 1. And now this becomes the identity matrix. And I have to do the same thing over here, meaning that this row becomes 1 minus 2 times 2/5, which is equal to 1 minus 4/5, which is equal to 5/5 minus 4/5, which is equal to 1/5. That is the first element. And the second element is 0 minus 2 times negative 1/5, which is equal to positive 2/5. So I have here 1/5 and positive 2/5. And here I have 2/5 and negative 1/5, which do not change. And so what happens is that now I have I is equal to this matrix, call it B, for example, B times A, which means that B is the inverse of A. is the inverse of A. In other words, B is equal to A inverse, which means that basically A inverse is equal to this matrix as 1/5, 2/5, 2/5, and negative 1/5. That is the inverse of this matrix. Now, alternatively, we can do column operations as well to achieve the same thing, right? So let's now do some column operations to do the same thing. Okay, so now let's do the exact same thing but using column operations on the same matrix. Now the matrix that I have is basically A is equal to basically 1, 2, 2, 1, 2, 2, negative 1, and I want to find the inverse of this matrix, right? So, and I want to do it, I want to find the inverse of A, through column operations. So since I want to do it through column operations, what I will do is that basically I can write my matrix as A is equal to I times A, or I can write it as A is equal to A times I. Since I want to do column operations, the column operations have to be done on the matrix on the right, and the matrix on the right has to be I, not A. Because if I do the column operations on A, then I will have to change A. But that's not what I want to do. I want to get this equation in such a way that I have my A on this side, and A is multiplied by some matrix, for example B, and that gives me some matrix I, for example, and then from that I can conclude that basically B is the inverse of A, right? And for the same reason, the column operations, I don't want them to be done on A. I want A to be left alone, not meaning untouched. So for the same reason, I'm going to take this equation, A is equal to AI. I'm going to do the column operations on A here on this side, and basically make it look like the identity matrix, so that I can have this side of this equation. And then I'm going to do the excuse me, I have to actually take this matrix here, because no, that's actually correct. The matrix on the matrix on the right is basically the matrix on which the column operations have to be done. And then I will do the column operations on this matrix I, and that becomes something like some matrix like B, and so this is actually wrong. And therefore I will have this equation in the form I is equal to, for example, A times B, and then from that I can conclude that B is the inverse of A, right? So I will take this equation. Now, when I take this equation, what happens is that I have A is equal to A times I. So I write this as A is basically 1, 2, 2, negative 1. This is the matrix that I want to look like I, and A is basically the matrix that I already have, so I don't want to touch that. And then the matrix I is basically 1, 0, 0, 1. And therefore, the column operations, I need to do the column operations in such a way that this matrix, in this matrix, this remains, of course, a 1. this becomes a 0, this becomes a 0, and this becomes a positive 1. So these three have to change, right? So what I will do is that first, let's see. It's not always easy to see the operations, meaning that if you do one step wrong, the problem with this method, one of the problems with this method, and probably the only problem, except that it's a tedious method, is that every step that you do is if you do it wrong, or in such a way that you're not supposed to do it, then it's going to change something else as well. Meaning that, for example, if I want to get a 0 over here, right? And if I want to get a 0 over here, if I do something on this column so that this becomes a 0, then this -1 changes as well. And then then I have to do something else so that this becomes a positive 1. When I do that, then this 2 changes as well, and so this can go in circles over and over again. You don't want to do that. So I will, as long as you have the solution, you can apply the solution. Otherwise, then you have to think a little bit so that you don't actually mess it up. So then I will just simply follow the steps that there are in the solution, and I will finish this exercise. Otherwise, I don't want to think about something that I don't really have to think about. So now if I apply here, so I have 1, 2, 2, -1, and 8 times 1, 0, 0, 1. And if I apply, for example, C2, becomes C2 minus 2 times C1, right? If I apply this here, what happens is that the second column becomes the second column minus 2 times the first column. So basically this becomes a 0, and this becomes something else. We will see about that. Now, so basically the first column, I can write it as it is, 1 and 2, and this becomes 2 minus 2 times 1, which is equal to 2 minus 2, which is equal to 0, and this becomes -1 minus 2 times 2, which is basically -1 minus 4, which is equal to -5. So this becomes 0 and -5, and this becomes A, and over here you have basically, again, the first column remains unchanged. The second column becomes 0 minus 2 times 1, which is equal to -2, and this becomes 1 minus 2 times 0, which is basically 0. So this remains as it is. So that's basically one thing that we can do, and as a result of that, now I have a 0 over here, and so these are the two elements that I need to take care of. Then what I can do is that I can apply C2. C2 gives basically -1/5 C2. -1/5 C2. And so as a result of that, this becomes a positive 1. So I can write this as basically 1, 2. 0 times -1/5 is basically 0, and -5 times -1/5 is equal to 5/5, which is equal to 1. Right? And that is equal to 8 times, and again the first column is the same, and that is positive 2/5, and that is -1/5. I have to multiply these by -1/5 as well. And then what I can do is that I can apply basically C1 gives C1 minus 2 times C2. So column 1, So over here right now I have my 1 over here, my 1 over here. That's what I want. This 0 is also what I want. This 2 has to change. So I write this as the column 1 becomes column 1 minus 2 times column 2. So, and that would give me a 0 over here, right? So column 1 becomes basically 1 minus 2 times 0, which is equal to 1. And basically 2 minus 2 times 1 is equal to 0. So this becomes 1 and 0. This becomes 1 and 0, and column 2 doesn't change. And that is the same thing as A times, again, column 1 has to change. So 1 minus 2 times 2/5, which is the same thing as 1 minus 4/5, which is equal to 5/5 minus 4/5, which is equal to 1/5. And then 0 minus negative 1/5 is equal to positive 1/5. Is equal to positive 1/5. So you get basically 1/5 here, 1/5 here, 2/5 here, negative 1/5 here, and that's basically that. Now what you have here is, so you have basically this is I is equal to A times 1/5, 2/5, 1/5, negative 1/5. And therefore you can say that if I call this matrix B, for example, you can say that B is A inverse, because B times A is equal to I. Therefore A inverse is the same thing as basically 1/5, 2/5, 1/5, and negative 1/5. That is basically what we were looking for. So let's do another question here as well. And I think we need a little bit of time for this problem. So I'm going to end this video here, and then we will do this example in the next video. Thank you.